Yes, hello? Is the sound, okay, the sound works, perfect. Thank you very much for coming for the Paul Ehrenfest Best Paper Award for 2022. Just as a reminder, the Paul Ehrenfest Best Paper Award for Quantum Foundations recognizes outstanding and influential research contributions to the foundations of quantum physics. And the aim of the award is to raise awareness for the field of quantum foundations and to draw attention to new and interesting achievements without delay, unless there's a pandemic, in which case there might be a delay. Ehrenfest, as you probably know, was born and raised in Vienna. He studied theoretical physics, and later in his life he went on to become a professor of theoretical physics at Leiden University in the Netherlands, a position which was vacated by Lorentz. He contributed extensively to many different areas of physics, and in particular quantum physics, as we know. So in 1916, he published his seminal paper on adiabatic invariance, and in 1927, the famous Ehrenfest theorem, which related the expectation values of quantum mechanical operators to the classical Poisson bracket. And he also made extensive contributions to statistical mechanics, kinetic theory of matter, gravitational theory, electron theory, and the theory of light and magnetism, which you may have heard from me last year. But my fun Ehrenfest fact for this year is that he also has a paradox. So the Ehrenfest paradox is about the relativistic description of the geometry of a rotating rigid disk. And he formulated this paradox in 1909, so shortly after special relativity. And in this paradox, there is a discrepancy between the Euclidean circumference versus the circumference calculated by special relativity based on Lorentz concentration. Maybe it's a transformation. So in the 10 minutes that I had to research this paradox, I could not find a solution to it. So today, in the spirit of Ehrenfest's scientific achievements, foundational and gravitational relativistic, we're here to celebrate the most significant publication in theory of experiment in the foundations of quantum mechanics, or for the call issued in 2022. So this year, the selection committee was comprised of Anne Broadbent from the University of Ottawa, Mohamed Buran from Stockholm University in Sweden, Tracy Northup at the University of Innsbruck, and Marcin Pawlowski at the University of Gdansk, together with us, the year group, Armin, Cosentino, and myself. And the committee decided that this year, the award for the best paper should go to Quantum Theory Based on Real Numbers Cannot Be Experimentally Certified, by Marc-Olivier Renou, David Trillo, Mirjam Weilenmann, Thinh, Armin, Tavakoli, Nicolas, Gisin, Acín, and Miguel Navascués. So I'd like to invite Mirjam to collect the award on behalf of her co-authors and colleagues. And Mirjam will now present the talk. It takes a minute.
Oh, okay. Okay. Okay, well, so on behalf of everyone involved, I think I'm going to say thank you. Of course, we're very happy to receive this award, I think all of us. And I'm also happy to now have the opportunity to tell you a bit about the work for which we got this award. Okay, not all the authors can be here today, which is, I guess, also why I'm collecting this. But I want to just introduce to you everyone involved. Okay, so this is everyone. Actually, David and Miguel are also in the room, so you can also talk to them later about it. And then there is also involved Marc-Olivier, Thinh, Armin, Nicolas, and Tony. Okay, so these are all the authors. And then, of course, we also want to take the opportunity to thank not just the committee for awarding us the prize, but also the various institutions that have been supporting us and are still supporting us. In this case, many of us actually have been or are still based in Vienna at the ICOCI, as well as the Atom Institute of the TU Wien. There is a group from Switzerland of the University Geneva and also the Constructor University in Schaffhausen. And there is a team based in Spain, in Barcelona, at ICFO. Okay, and so thank you very much. And now I'm ready to tell you a bit about our work. Okay, I have to say I see many experts in the room, so this is a talk for non-experts. So maybe we can have another discussion afterwards as well, if you're interested. Okay. Okay. So first of all, it was a very happy surprise for us to actually find out that Ehrenfest actually cared about exactly the question we were tackling. Okay. So he had a paper in 1932 where he was treating a few questions regarding quantum mechanics, and actually the first thing he pointed out is the imaginary unit in the Schrödinger equation and in the commutation relations. Okay, this is something that he cared about, and it interested him how to understand this. Okay, and at the time he was also not the only one. There is also, for instance, a letter from Schrödinger to Lorentz where he is also concerned or dissatisfied with the fact that the wave function in quantum theory is not a real function. Okay, so now why would one not like this? Okay, so you can say, okay, but maybe you've studied physics, and actually complex quantities come up all the time when you do physics. So maybe it's not that new. Okay, so and the standard example could be an electromagnetic wave. What do you get there? Well, you get the electric and the magnetic field, and you can write this in terms of this complex exponential. Okay. Now the point is that in these cases, whenever you speak about your observations, what you really do is you take the real part. Okay. So while this comes from solving some differential equations, where the complex exponential is the standard ansatz, somehow when you speak about what is really physical, you speak about real things. Okay. And you can somehow see this as some kind of a mathematical trick that just helps you to get to your final result. Okay, and now I think what this satisfied the physicists at the time, that the same is not true in quantum theory. Okay, you have a complex wave function, but when you observe something, you don't just take the real part of the wave function and say this is what I have physically. Okay, and so not in the same way as here can complex numbers just be seen as a mathematical trick that helps you to get around your formalism, but really it's in the wave function, and it has to be understood why it's there somehow. Okay, and Ehrenfest also gave an explanation, not exactly like this, but it boils down to the same gist, I would say, in his 1932 paper. Okay, but now seeing this, okay, I'm telling you, okay, you can't just do the same trick in quantum theory. But of course, what you can then ask, well, could there be a different way in which the complex quantities are actually not needed in quantum theory? Okay, so this trick is not it, but there could be other ways. Maybe we can formulate quantum theory just with real quantities. Maybe complex is not needed. Okay, and now to show you in which sense we tackle this question, I have to introduce a bit more of what quantum theory is. So many of you will know this well. For those who are not experts, you can also just think about systems that I send to detectors throughout the talk, and you can just imagine that as mathematical object, I assign some matrices to these systems that capture their properties, okay? And the properties are found. Okay, now a bit more technical, these are density operators on complex Hilbert spaces. We have to describe how systems evolved. So we have to see if I take my system, I let it evolve for a while, it may change some of its property. So after the evolution, it will be in a different state, and this can be described by a unitary transformation. And we measure the systems, okay? I will choose here a formalism where I index measurements with X and outcomes with A, okay? And I will use observables. And then you can imagine that to each measurement, to each detector where I measure, I assign essentially one of those operators for each outcome that I have. Okay, And I can then compute the probabilities to get the outcome, given that I've chosen the measurement I'm interested in by taking this trace. Okay? Okay, and so this is what you can do with a single system. You prepare it, you let it evolve, and you measure it. But now we also need to say what we do when we have several systems. Okay? And in fact, the composition of systems in quantum theory is given by the tensor product. And when we have systems that are prepared far apart, somewhere in the universe, what we assume is that they're independent, and then we say we have a product state, and that's written in this way. Okay? So this is what I'll consider, the formalism I consider for quantum theory. And now one way to go to real quantities in this way is I can just ask, well, instead of these complex Hilbert spaces, I can ask there to be real Hilbert spaces. Okay? So essentially, it looks the same. If you think of these things as matrices, you just replace the complex entry with real entries, and you're at the formalism we have now. Okay? So states now live on real Hilbert spaces. The transformations become orthogonal, and you have here symmetric projectors. Okay, so these are the two theories we're considering, and we'll compare. Okay? And so this would actually solve the problem. So if I can describe any problem that I have with this formalism, I think Paul Ehrenfest would be happy with me, because actually it means I don't need any complex quantities anymore. I can really do everything just in a real formalism. Okay? And what the title kind of tells you is that we're going to show that this is not possible. Okay? Now, first of all, when I write this down so formally, the two theories look very similar, okay? But the mathematical structure that we have in real and complex Hilbert spaces is actually quite different. And this also shows in kind of more operational and more experimental ways, okay? And this I want to show first. So let's first look at the simple experiment. Let's look at the smallest system in each of the two theories, okay? So in quantum theory, this is a qubit. So this has a state that is essentially specified by 3 parameters. And you can map this nicely to some vector in what is called the Bloch ball. Okay? So these are the Pauli matrices. Okay, now if you know about the Pauli matrices, then the X and the Z one are real, but the Y one is actually complex. And so essentially what happens if we take the smallest unit in real quantum theory is we lose that one. Okay? And we just have 2 of the 3 degrees of freedom left. Okay, so what this means in this Bloch sphere picture is we restrict ourselves to just the XZ plane. Okay, now what do I do if I want to find out which state I have? What I do is I perform measurements, and one way to infer everything in this case is doing exactly the Pauli measurements. Okay, so if I do X, I will infer X. If I do Y, I will infer the Y here, and if I do Z, I infer the Z. And in real quantum theory, I just have 2, okay? But this now seems very similar still, because it's just that I have a slightly smaller number of parameters, but somehow it's the same. Okay, but this is different when we look at larger systems. Okay, so let's look at this state. This is a quantum state. Now, if we're in the product space, we just can get now a basis in terms of all combinations of X, Y, and Z. Okay, and now here some of the coefficients are 1 and -1, and the others are all 0. So you get this state. Okay, now what do I do to find out if I get a system that I have this state? Well, I try to do the same. I do all combinations of X, Y, Z on one system with X, Y, Z on the other. Okay, so I prepare many copies. Each time I choose a combination of measurements, and I do all of them. Okay, so now what I can do then is I can really find all the coefficients in my state, and I can find out again which state I have. Okay, and this is what is called tomography of a quantum state, or local tomography. Now, the thing you may have realized is that actually this is also a real quantum state, okay? Because while the sigma Y Pauli matrix is a complex matrix, if you take 2 together, it becomes real. And so in fact, this is also a allowed state in real quantum theory, okay? But now we have a problem, because now in real quantum theory, we cannot do the sigma Y measurement, okay? We can do X and Z. We will find all the coefficients actually except this one, okay? Because we just can't do things on individual systems. So what you need in real quantum theory is actually a way to measure the 2 systems jointly, okay? And this is what is called non-local tomography. So you cannot figure out all the degrees of freedom in a joint system by just measuring the individual parts. But whenever you go to a larger system, you need kind of new types of measurements. Okay? And I would argue that also on a physical level, this is now quite different, because in one theory, you can do everything locally. In the other theory, you get new degrees of freedom as you go to larger system. Okay? And so this is somehow how this difference in the Hilbert space structure also shows in the physical world. Okay? So, and this is one way this exhibits, and that we can see that the two are different. Okay. So now, then I've now made the point why they're very different. So then you may ask the other way around. Well, why would I now think I cannot be able to distinguish them? It's obvious they're different, right? And to see this, I actually have to take a step back and tell you what we mean by really ruling out the theory and distinguishing two theories, okay? So what we can think of in this way of thinking that I've already introduced is that we have a system that is somehow prepared, it's in a state, and that is measured. Okay, so there is an experimenter that has built a detector with some knobs that I can change that chooses what the detector does and measures the system. Okay, and for each of the measurements he chooses, he gets some outcomes, and this will give some statistics. Now, what I need to be able to say that I can distinguish a theory or falsify real quantum theory is somehow a statistic that I can produce if I describe this experiment with complex quantum theory, but that I cannot produce if I describe it by real quantum theory. Okay, and this is what we often call device independence as well. Okay, so this is what I really want to have. Okay, now how could I do this? Well, let's think about an example first. Okay, so you can think, for instance, that this particle is, let's say the polarization of a photon or an electron spin, and this can be modeled mathematically as a qubit. Okay, this is the same as we've seen before. So in complex quantum theory, this is a qubit. Now, a way I could want to build my detector is that I choose my measurements to be the Pauli measurements, because then I know I can figure out these parameters. And these Pauli measurements all have two outcomes, +1 and -1. So what I really will observe are these statistics, okay? For +1 and -1, that will depend on x. Okay. Now, if I were to model this in real quantum theory, well, okay, if I want to model this with the rebit, what I can do again, I just lose the complex part, okay? And so I really only have 2 degrees of freedom. So now I have, in one case, 3 degrees of freedom, and in one case, 2 degrees of freedom. So again, I could think, okay, now this I can distinguish, because I can do enough preparations here, so I will see in my detector whether, in fact, I have 3 degrees of freedom or I have just 2 that can vary, okay? But the problem with this is that somehow going from the fact that my physical system, for instance, an electron spin, is described by a rebit is quite a step. Because it could be that it is described in real quantum theory, but by a different type of operator. It's not clear that because in complex quantum theory, I use the qubit to describe this system. In real quantum theory, I need to use the rebit. It could be a very different system. And so really what I want to know is whether I can have here any way to describe state and detector in real quantum theory that leads to the same predictions as we have in the complex case. Okay? And it turns out, actually, there is a way to do this here. And it's a quite nice construction, so I will show this. Okay, so in fact, what we can define is this state here, where the star denotes a complex conjugate, okay? What it means for a state to be real is that when you take its complex conjugate, it remains the same, okay? And this happens here, okay? Because if you take the complex conjugate here, you get one, and this one is removed, because if you do it twice, it goes away. Okay, and the same happens with the measurement. Okay, so now I have given you a state that is valid and a measurement that is valid. And now we have to argue that really these give exactly the same as if I had done the complex formalism with the state rho and the measurement A. Okay, now to argue this, I think it's helpful to give some intuition. So of course, this is just one system that this corresponds to. but it's actually helpful to think of it as made up by two hypothetical systems. Okay, and the second one is kind of what I call a control system, and in fact, it's in this state. Okay, and so what I can think of this is that somehow this system determines whether I take rho or I take the complex conjugate, and it does the same for the measurement. Okay, and the way I've chosen this is in a way that whenever you take a tau with a tau, it remains a tau, but if you take a tau with a tau star, you get nothing, okay? And so what this means is that you can match up here the A with the rho, and the rho star with the A star, and because if you have everything complex conjugated, and it gives you a probability, this is anyway real, so it doesn't do anything, you can in this way actually reproduce the same predictions as if you just had rho or A, okay? So because tau satisfies these relations, you can see that if you put them together, you get the same predictions as if you had used the complex formalism with these. Okay? And this is a construction that has come up many times in the literature. For instance, it was used by Stückelberg in the 60s. This is the first occurrence that I know of it. Okay, and so in this experiment, in any such experiment, this works for any rho, not just for our example. You can, in fact, simulate everything in real quantum theory. Okay, now this is nice. Now the expert among you may say, why have we gone all this way? Because of course there is another way to do this. So in this particular scenario, what I could also have done is I could have built my detector with that when a system comes in, it throws the system out, but it also has some classical input where I can send some information. So what I can do is I can just send the information of what I've prepared here. And then, depending on which measurement I want, because I have the full information what should come out in this case, I can just give the right statistics, okay? So there's a very simple way to just send classical information and in fact do everything, okay? So in fact, any probabilities we could get here, we could also get with such a toy detector that really doesn't do much, okay? And so somehow the real construction in this particular case was not useful, but I did it here because it will come up again later. And also because now, looking at this classical case, it kind of brings us to think about, okay, in this case we can simulate everything, but we know of scenarios where we cannot, namely in the Bell scenario, okay? Because there, exactly what we do is look at just statistics and infer that something is not classical, but quantum, okay? And so then this is what we go to next. So we have here Alice and Bob, who share cat systems from a source, so it sends some to Alice and some to Bob. And they both have detectors that they can operate. So Alice chooses some inputs and gets some outcomes again, and Bob as well. And now we assume that they're far apart and independent, so they are in this tensor product. Okay? And Alice gets the A system here, and Bob the B system, so they both have a subsystem that they will measure. Okay, and now the question is, well, with these statistics now, is it still the case that we can reproduce everything classically? And this we know from Bell inequalities that it's not, because we can violate them. And so in fact, we have something like this cartoon. So we have here just a cartoon of what the sets of possible statistics here could look like. And what we see is that when we have classical probability theory, we have strictly less of those than in quantum theory, okay? And the Bell inequality here would be one of those facets. Okay, so this we know. But now this gives us hope, because before all these theories gave the same predictions, but now these two at least split, so it could be that real quantum theory now also gives something else. Okay? Now, what turns out to be the case is that we're not lucky, and this doesn't happen. And in fact, this is now based on the same construction, which is why I already introduced this. Okay? So we use the same measurements controlled by this tau state. But for the state, we need to make a slight adaptation. So what we do now is we actually prepare two of those tau states, but in a correlated way. So Alice and Bob always either both get the tau, or they both get the tau star. Okay? And what this means is that what the tau does is somehow in a correlated way match up the measurement operators with the state and the complex conjugates together, okay? And this way, again, we can simulate anything. Because of the properties of the tau, we can show that we get exactly the same thing when we use these real operators to describe the state and the measurements. Okay, so this is a construction that actually was, as far as I know, first introduced in this paper by McCaig, Mosca in Gisin in 2009. And this is now actually the reason why people thought there is no difference between the two. Because whenever you have such a source, you can add as many parties as you want. You can have a Charlie and a Dave as well. You can do this construction, just adding here a few more of those taus. And you will always be able to simulate anything that you can do in complex quantum theory with real quantum theory. Okay. So this is where we were at. And indeed, this shows in this cartoon that quantum and real quantum behaviors are the same. Okay, and now our result kind of shows that this changes when we look at networks. Okay, you have a network as soon as there is more than one source of systems here. Okay, so in this case, we have Alice, Bob, and Charlie, who each operate a detector and get systems from two different sources. Okay, so actually Alice then will do a measurement on her system A. Bob will actually get two systems, so one here B1 and B2. And so he can do actually a joint measurement on B1 and B2. And Charlie gets the last system. Okay? And because everything's again separated, we can assume that they're independent and take this tensor product form. Okay, so this is the setup. Okay, and now what we do is we show that in this setup, there is such a behavior, such a statistics, that we can get in quantum theory, but that real quantum theory would predict cannot exist. Okay? And so this is then also what allows us to propose an experiment, because if we find these correlations experimentally, real quantum theory can actually not predict the right things in that experiment. Okay? This is the idea. And we do something slightly more general. We also allow these two sources to be synchronized. Okay? Because this is a classical thing, I symbolize with a coin. Okay? And this is actually important, because when we actually later want to do the experiment, what we'll want to do is we will somehow want to have a clock that synchronizes everything that is going on. And we want the sources at the same time to give us states so that we know kind of what belongs together. And so for this, somehow, this clock gives some information, classical information, to all the parts. And so this is something we actually should have. From a mathematical point of view, it also makes those cartoons nice and convex, so it was easier for me to draw. And it's, of course, a stronger result as well to allow this for real quantum theory than if we were to not allow it. So it's advantageous in very many ways to have this. Okay, so now what I want to do is I want to give you an intuition how to construct this point. Okay? Okay, and so at the high level, I think it's a two-step procedure. The first one is that somehow to do this, because we know there are these simulations in the Bell scenario, we have to have something where Bob doesn't act on the system he shares with Alice and the system he shares with Charlie separately, because otherwise we would have two Bell scenarios next to each other and we could simulate everything. So what we need is that he does something entangled, essentially, and what he does is entanglement swapping. Okay? What this means intuitively is he does an operation on the two systems he has. So let's assume he shares an entangled state with Alice and an entangled state with Charlie. And now he does an operation that kind of transfers this entanglement to be afterwards between Alice and Charlie. Okay, so he kind of transfers this over. But what this also does is, because he's in the middle here, it blocks this construction that we had before. Because if now you imagine this source shares taus and tau stars, and this one as well, well, sometimes these will match up, but sometimes Alice will get a tau, and Charlie will get a tau star, essentially. Okay? And so what this means is that while somehow, by doing this, we share an entangled state between Alice and Charlie, so we're somewhat back in the Bell scenario, we also block the construction that we had before, okay? So this is why this is here, okay? And then once we're in the Bell scenario, we want to do something that is very complex, okay? Something that we hope we cannot do with real numbers. So it should be something at the border of the quantum set, and something that potentially involves Pauli measurements, because there we know we have one that is really complex. Okay, and now for the expert, I tell you exactly what we do. Okay, so what we do is we do a Bell state measurement. We have maximal entangled state, actually 0, 0, plus 1, 1 here and here. We do a Bell state measurement in the middle to swap the entanglement. Then we have 3 settings for Alice and 6 settings for Charlie. And what they correspond to are the Pauli measurements for Alice and kind of tilted versions for Charlie, okay? And if you look at this, you can see that if you look at always pairs, so for instance, 1, 2, and 1, 2, this essentially is what you have when you violate CHSH maximally, okay? And if you look at these and the last 2 as well, and so it's like having overlapping CHSH games, okay? And this idea actually was not ours, but comes from this paper, because what is shown here is that in the Bell scenario, you can self-test Pauli measurements this way, okay? And this captures this intuition that you want something that cannot be reproduced in many ways, because if you self-test something, it means that essentially there's only one way to get specific statistics, okay? And so this is why we use somehow the self-test to do this, okay? And then using these measurements and states, we can compute what statistics we get, okay? And then the next step is to prove that these cannot be achieved in real quantum theory, which relies on the self-testing argument, as well as some insights on entanglement theory on real Hilbert spaces. Okay, but I won't go through the proof, but I will show you the theorem. Okay, so this is really the theorem we have. So if Bob has roughly all 4 outcomes with equal probability, and for each of them, we are close to 6√2, which corresponds to a triple CHSH inequality, which is playing these 3 CHSH games that I've shown you in the measurements in each case. Then we can show that indeed there is no decomposition in terms of real states and real measurements. Okay? And here the lambda is the synchronization or randomness that I introduced, that we also have. Okay, so this is the main thing. And you can see here that we have here this epsilon. So if we're kind of very slightly below this optimal value here that the construction before achieves, we can still see that we cannot reproduce it with the real quantum theory. So actually, this is a robust thing. But it's not good enough to do an experiment, because there is a gap of 10 to the minus 5. And the gap is not large enough to really check this. Okay? And so this is why we went on and actually got a stronger result, which shows that indeed there is actually quite a large gap between this optimal way that we know how to achieve and an upper bound on what we can achieve in real quantum theory. Okay, so we know that anything that real quantum theory can do is somehow on this side of the line. Okay, and in this case, what this relies on is a convex optimization technique from this paper, and that is combined with realizing that if you transpose one subsystem of a real separable state, in fact, because these subsystems are real, if you transpose it, nothing happens. So when you transpose a subsystem, you get the system back. Okay, and combining these two things, we get kind of upper bounds on what you can do with real quantum theory. Okay, so these are the results, and now with this, actually, we're ready also to do experiments. And indeed, there have been several. So the first implementation was with superconducting qubits. This is a schematic of the setup. So we have the 2 sources. 2 are sent to Bob, who does a Bell state measurement, and then there is Alice's and Charlie's measurement. And indeed, what they found is that somehow the statistics they get are in this range where real quantum theory could not explain them. Now, there is some issue with this because this actually all happens on a chip. So these different systems are very close together, and so they are also coupled. Okay, so and somehow in this setup, it is kind of difficult to argue that really you have two independent sources, 1, 1, 2, and 1, 3, 4, because there is a coupling here. Okay, and so in that sense, it's hard to argue that really this network assumption that is so crucial for the setup we have and for this to work has been fully implemented, and so what remains open here is what we call then a locality loophole of taking them really apart and having two independent sources. There have also been 2 experiments with photons. The first one we were actually also involved in. What we did is we kind of changed Bob's measurement a bit from a Bell state measurement to one where you kind of do partial Bell state measurements, but several of them, because this was more tractable. And this is the setup. So this is on an optical table with 2 sources, Bob, Alice, and Charlie. And afterwards, there was also another one where instead of putting this all on a table, they actually separated the different systems much further. Okay, in both of these, there remains a detection loophole open, and because we were involved here, I know a bit more how this works here. So what we did is we could only get essentially the statistics for some of the outcomes, and so for the other outcomes of Bob, we had to infer them indirectly, and of course this would need to have to be overcome in order to really have a kind of loophole-free test. Yeah. Okay, I know less about how it goes there. I believe they actually split it into 4 cases. So they do the four settings of Bob separately. And but this has to be taken with a grain of salt. I don't know this so well, but I'm pretty confident that they didn't close it either. But the locality loophole is okay. Okay, so, but what is kind of nice for us is that really, I mean, this has interested experimental groups as well, and somehow 3 experiments were done quite soon after we brought this out, and even though not all loopholes have been closed at the same time, all of them have been somewhat closed at some point, and I think this is actually good evidence that it will also go through once someone does the full thing, okay? And so I think for us this is pretty nice and can be seen as evidence that it is actually possible to experimentally refute real quantum theory, where I still kept the question mark just in case. Okay? Okay, so this is all. So what I've shown you is that what we showed theoretically in the paper that we're also discussing here is that indeed quantum theory over real and complex Hilbert spaces don't make the same predictions for experiments when we have these networks, okay? And we've also seen that, okay, quantum theory over real Hilbert spaces can actually not explain what we find in some of the experiments. What is still missing is what we just discussed. So a fully loophole-free experiment has not been done. And the other thing I think is quite exciting for the foundations community is somehow these analyses of quantum networks are still relatively new. And I think with this it shows that also not just for distributing communication, also for foundational questions, it can give new insights that before were not possible, because we really relied on tools that came from looking at networks. And so I think this is actually a big chance for the foundations community and for us to see in the future what else could be gained with such approaches. I think there is a lot to do, and with that I would like to thank you, and yeah, I can answer questions.
Are there any questions? I have one.
Okay.
Do you have any idea what one might do with these correlations?
What with the ones that you cannot get?
Maybe some kind of I was just thinking BB84. You only need X and Z measurements there. So maybe there are cryptographic key distribution protocols that could be.
You can do device independent distribution, and then in the middle is a repeater. You can do it like this.
Yeah, so the thing I'm not sure is that you'd really want necessarily the X, Y, Z there, because often they rely still, even if they swap entanglement, they still rely on the CHSH game.
It's true.
And okay.
But you could be, potentially you could get a higher secret key, I guess.
Potentially. So I at the moment see it more as a theoretical thing, and I think the networks in general give us a lot of options, but I'm not sure exactly these correlations will.
So do you know whether this behavior happens also for other Bayes inequalities? Because this one is very peculiar because it comes from the self-testing protocol. So do you have any ideas of other type of inequalities where it is?
Yes. Okay. Yes. So what I know is that what we've actually tried, especially David, I think, is that you can also do this with what is called an elegant Bell inequality. So there, actually, you can reduce the number of settings here to 4. Okay, and you can also get a gap between real and complex. I think the gap was not. We hoped at some point that this would be a better gap for testing. I think it didn't look like it, but certainly you can put other Bell inequalities there, and you can get a similar behavior.
So, but do you have any idea of the structure of the mechanism, or just, or you tried? Okay, the one I said was very peculiar. Also, the elegant Bell inequality. Why you just try a few inequalities and it works for some of them?
Yeah, actually, I think we tried those too. So.
Okay. Okay, but by chance you work on both, so it's a very common thing.
I mean, you need at least. So one question is whether you could actually that we don't know is whether you could do it. Sorry, with 3 inputs on both sides. So actually what we wanted to go for is smaller scenarios with as few as possible settings. And there, okay, we know 3 and 4. We don't know if 3 and 3 works, for instance. I don't know if there you can say, if the Bell inequality looks like this, you can do it. And if it,
searching for these inequalities.
I don't think we have really tried this.
One intuition is that you have an inequality. Real quantum Bell violation is done in systems that have a higher dimension than the complex quantum violation. Strictly complex, strictly higher. Once you do this, then you realize that it's impossible to distribute that state if you just have two states and you make a measurement in the middle with only d squared outcomes, where d is the dimension of the complex thing. So that's more or less the intuition why it doesn't work. Actually, you could actually probably perfect correlations if you did an eight outcome measurement in the middle in all the examples that we have.
Very last question. You had a coin before. Where
Yes.
Where does this enter?
Here.
So this is another loophole in the experiment, I guess, right? Because if you need to time the distribution of this.
So I'm saying that the proof still holds if I allow this, actually. So I can say that the distribution I construct here.
And you need that for the convexity, you're saying?
Well, I don't. Okay, the convexity is nice, but so I do here the construction of the complex behavior. But then I say for the real behavior, you can even allow a coin here,
okay.
and it will still hold. And so in the experiment, we actually have the coin. So it's kind of important to say in this case, we could still not achieve it with real quantum theory, because yes, otherwise it's exactly how you said, no. It would open up that it just comes from that.
But the coin in the experiment is done how?
It's kind of a clock that, so I don't know how they do it in the superconducting one, but in ours, so there is a synchronization that makes sure that the sources send photons essentially at the same time to Bob. And this clock, of course, is some classical information that is shared with both of them. And this could be modeled as a coin in that sense.
Does that open another loophole if it's not quite synchronous?
What you're saying, like if they would have a memory and you would somehow keep it. Okay, I mean, I'm not sure. So I think if you, okay, it depends. I think if you would close the detection loophole and really make sure in each time interval only one thing is sent, probably you could close that. I don't know in this particular case in what sense it would. Maybe Miguel has another insight.
The question is why.
So there's a coin and there's something to times the